Swayam Prabha. Digital India. Educated India.
So to do that, if you just look at this equation, set of equations, it's the same equation, there is no difference. So what we have done, it is du by dt. Instead of writing all the set of equations or the total acceleration in terms of temporal as well as convective accelerations, so what we have written is the total acceleration, that is du by dt, which is nothing but dou u by dou t plus u dou u by dou x plus v dou u by dou y, all that. Okay, so du by dt is the total acceleration, is equals to gx is the body force in the x direction minus 1 by rho dou p by dou x is the pressure force in the x direction. Then you have mu by rho del square u. What is this del operator? Del operator is nothing but your dou by dou x plus dou by dou y plus dou by dou z. So if it is del square, it is dou square by dou x square plus dou square by dou y square plus dou square by dou z square, and operated on u will give you that equation which we had written in our previous slide. Okay, this one. So this is nothing but your del square u. Okay, similarly this is going to be del square v, this is del square w. Okay, so that is what we have written here. All right, now still you have these three equations. Now if I write down in vectorial form this u, v and w, I'll write down that as v, capital V, which is a vector, nothing but it is a combination of u, v and w in the respective directions. So I can straight away write dv by dt, which is capital V, is equals to g x or g, that is the vector corresponding in the corresponding directions, minus 1 by rho del p. Okay, so this del is again, if you see, dou by dou x, dou by dou y, dou by dou z. So depending on the direction that you are trying to resolve, this term is going to come up. And here again similarly you have mu by rho del square v. So if you are talking about x direction, u is going to come. If you are talking about y direction, v is going to come. If it is z direction, w is also going to come. Okay, so finally we can write down this simple compact equation, which is nothing but your momentum equation of motion. Okay, and in addition you have this continuity equation which needs to be used to solve all the flow variables. All right. Okay, now having understood this, as I said just some time before, that this Navier-Stokes equation is applicable for real fluid flow problems or to solve real fluid flow problems. Now, if I have some place where I want to solve the flow which is considered as inviscid, or I really don't have to solve or address the viscous effect of the fluid flow, in that case I can neglect this part, which is basically the force exerted due to the viscosity of the fluid, or the viscous force can be neglected. Now if I do that, the equation that I'm going to get is nothing but your Euler's equation. So we'll see that. So Euler's equation is applicable for inviscid flows. So basically it is, you can, in other words, you can tell that it is ideal fluid, so where viscosity is not there. Okay, so the moment we say that the viscous effect is negligible, when we are not solving that mu by rho del square v term, then we can call it as Euler's equation. Okay, so for Euler's equation we will not have the viscous term here present. So all three different directions we can write down the terminology. In addition to this, we will also solve the continuity equation, because still we have four unknowns. So we'll have to solve four equations, and all these four equations are nothing but your Euler's equations. Okay, now the same Euler's equation you can also, we have already derived the Navier-Stokes equation, and from that we have come all the way here. But somebody wants to rewrite the whole thing or derive the whole Euler's equation in a different way, that also is possible. So let us, for that, you take one fluid element. Again, I am just taking a fluid element. In this, you can either take P here, and the pressure here is going to be P plus dou P by dou x into dx. Or if I take the P pressure as pressure P at the center, then on this side it is going to be P minus dou P by dou x delta x by 2 applied over the area dou y dou z, delta y delta z, and on this face it is going to be P plus dou P by dou x multiplied by delta x by 2 applied over the area delta y delta z. Okay, so it's all same, there's no difference. You do this way or that way, finally the solution is going to be unique. Okay, so now let us consider this, which is basically an element having delta x, delta y, delta z as the dimension in respective x, y, and z directions, and the body force that are acting, the body force of this fluid element is noted here as x, y, and z in the respective directions. Okay, so it is the body force per unit mass. So now in this case, weight may be taken as a component of G, since force per unit mass is equals to acceleration. Okay, so now taking this, let us resolve in the x direction. Okay, so we will write all the forces acting in the x direction and equate it to mass into acceleration. All right, so if you write it down, this is what is your expression. This is nothing but your mass rho delta x delta y delta z is the volume, so multiplied by density gives you the mass, multiplied by du by dt is nothing but your acceleration. Okay, this is total acceleration. So mass into acceleration is equals to the force. What is the force? We know already there is a body force. So body force is basically the mass and the weight, basically unit weight of that. So it is, let us say delta x delta y delta z is the volume multiplied by rho into g, or g in that direction is nothing but your unit weight of that mass. Okay, or of that fluid element. So this is your body force, plus we are talking about the force in the x direction. So the force in the x direction due to this pressure is going to be positive. So P minus dou P by dou x delta x by 2 dou y dou z is going to apply the positive force on this fluid element. Now the pressure here is going to generate a force which will be negative x direction. So that's why it is minus P plus dou P by dou x delta x by 2 multiplied by dou y dou z. Now if you resolve this whole thing, if you see here, delta x delta y delta z is present here. In each term there is delta x delta y delta z, as well as here also delta x delta y delta z. So now we can take that out or divide by volume. Okay, so if you do that, or you divide by the unit or divide by the mass, take the rho also down, then you can write down dou u by du by dt, that's the total acceleration, is equals to x minus 1 by rho dou p by dou x. Okay, and similarly all three different equations in three different directions can be written. Now same thing we had already derived earlier. So you do it that way or this way, you will come down to the same equation. Okay, so finally we could write down the dv by dt is equals to force or the body force minus 1 by rho del p. Okay, so this is what is your Euler's equation, and this equation or this term which we have written here, v dv by dt, is nothing but your acceleration, that is force per unit mass. So what we are calculating is the acceleration. This is acceleration only given, but it is not only acceleration we are equating, we are actually equating the force per unit mass. So somebody will tell that how could you equate the acceleration to force? No, we are still equating force, that is force per unit mass, to the forces that are also represented here, that is per unit mass. Okay, so both sides are equal, there is no difference. All right, now having understood this, which is the Euler's equation of motion is for ideal fluid. Okay, now this Euler's equation we will now take it forward and derive the Bernoulli's equation or the energy equation. We have seen the continuity equation, we have seen the equation of motion or momentum equation, and then now let us derive or see how this energy equation is derived or explained. Okay, now to look at that, let us quickly proceed to Bernoulli's equation. There are certain conditions that you should understand. Bernoulli's equation we are deriving using the Euler's equation of motion. So all that concepts that we have discussed that are applicable for Euler's equation of motion are valid also, or are applicable for Bernoulli's equation. Okay, so Bernoulli's equation is an approximate relation between pressure, velocity and elevation. We'll see how they are related or how the equation is correlating all three of these. Okay, now it is valid for irrotational flows and in region of steady incompressible flow where net frictional losses are negligible. The moment we say that okay, it's inviscid, okay, so the friction is negligible. Okay, it is not, there is no viscous effect, so the friction is going to be negligible. So that's also applicable. Okay, so please remember that it is valid for irrotational flows as well as steady and incompressible flow. Okay, so integration of Euler's equation between 2 points will give you the energy. Okay, now we will do the integration, but before that the force per unit mass multiplied by distance is nothing but your energy. So we are taking force per unit mass, then multiplying distance, so we will get energy per unit mass. So force into distance is energy, but because we are taking force per unit mass, what we are getting is energy per unit mass. Okay, so that is the basis for Bernoulli's equation. Now, in other words, if you say that the total energy, we will have different energy, we will see in the next slides, but let us say total energy is nothing but your kinetic energy, potential energy, and there is a energy due to pressure. So basically the energy spent by pressure to move 1 unit weight of the liquid, okay, is nothing but the pressure head or pressure energy that we are talking about. Similarly, the kinetic energy which is related to the velocity. So the kinetic energy used to move 1 unit weight of liquid is nothing but your energy that is considered here. Okay. Similarly, potential energy. So we'll see that as we move on and derive different terminology. So the gravity or the potential, what we are talking about, you can, this is just a notation, you can write it in any way. So the potential, let us say, is omega, that is equals to plus gh. So let us say the height, at some height you have the liquid, so the potential energy stored in that is nothing but plus gh. Okay, or the force per unit mass that's in any direction is given by negative derivative. So now that we have already discussed during the potential function, so I am not going to spend more time on this. So we are taking that x, that is body force in the x direction, is nothing but the negative derivative of this potential, gravity potential, minus dou omega by dou x. Similarly, y is minus dou omega by dou y. Z is equals to minus dou omega by dou z. Okay, now we have written this in one single term, that is gravity potential omega. Now let us substitute this and write down the Euler's equation. So if we write down the Euler's equation, we could write down that the force per unit mass or the acceleration that we have written here is equals to the body force and pressure force together. Okay, and this gx, earlier what we used to write, or x, is given as minus dou omega by dou x. Okay, so now as we have already discussed, this is a irrotational flow, and we know for the conditions that we have discussed, the potential flow theory is applicable. So if you remember, we had written that in potential, when we have the potential function, u can be written as minus dou phi by dou x, v is minus dou phi by dou y, and w is minus dou phi by dou z. So if we can write down this, then you can quickly tell that the value of u can be substituted using this phi. So let us say the value u here, that is only in dou u by dou t term, will substitute with this expression, that is dou phi by dou x, minus dou phi by dou x. So now similarly, we know the flow is irrotational. So if you write down the terminology, then we know that omega, which is the rotation, omega x, omega y, omega z, are supposed to be 0. So if it is 0, So we can write down that, if you remember, omega z is equals to dou u by dou y 1 by 2 multiplied by dou u by dou y minus dou v by dou x. So that if you equate to 0, you can write down dou u by dou y is equals to dou v by dou x. So similarly, you can write down this expression dou u by dou z is equals to dou w by dou x. Okay, so based on the irrotationality condition, we could write down these expressions. Now let us make use of this. I am going to substitute this dou u by dou y using this expression. So I will substitute with dou v by dou x. Okay, and this one, that is dou u by dou z, I will substitute with dou w by dou x. So basically all the denominators are going to be dou x, so that it will be easy for me to integrate and find a solution. All right, so that's the whole idea. So now once we have this, let me rewrite this expression. So I could write down minus dou by dou x multiplied by dou phi by dou t plus u dou u by dou x plus v dou v by dou x plus w dou w by dou x. That's equals to minus dou omega by dou x plus minus 1 by rho dou p by dou x. Now I can integrate the whole term with respect to x. Okay, so before integrating, I have written this expression, so which is, you can see all the other terms are same except this u v w term, that has been written as dou by dou x of u square by 2 plus v square by 2 plus w square by 2, and this is written based on the expression that we can write down v dot v cross del v is equals to 1 by 2 del v square minus v cross del cross v. So now here, because the fluid is irrotational, this term will vanish, the cross product is going to disappear. So we have only this. So based on this, we could write down, or we could convert this expression like this. All right, so that we will take it and integrate now. Now if I take that same equation and integrate with respect to x, I can write down, so this integrated, I'll get p by rho, which is, if it is brought to the other side, it will be positive. So p by rho minus dou phi by dou t plus these three terms together I am just noting down as v square by 2 plus omega is equals to some constant. So this whole integration will also give rise to some constant, and this constant could be a function of y, z and t, because this whole thing is function of either x, y, z and t, and because we are integrating with respect to x, the constant could be a function of y, z and t. Now similarly, if we derive the expressions for y direction, I can write down this, I will be able to get same expression with a constant which could be a function of x, z and t, and in z direction I will get a constant which will be a function of x, y and t. So now in all these three cases, the right hand side, if you see, all three expressions must be equal. Okay, so this right hand side must be equal because this left hand side in all these three cases it is equal. So if all these three have to be equal, then they cannot be function of x, y or x, z or y, z. They can only be a function of t. So therefore the right hand side is either a function of t alone or it's a constant. Okay, so now we can rewrite this expression as p by rho plus dou phi by dou t plus minus dou phi by dou t plus v square by 2 plus omega is equals to a function of t or it's a constant. Okay, so this is nothing but your Bernoulli's equation. All right, now let us try to slightly simplify further and apply to some different problems. Okay,